Okay, I'm going live just to go through some stuff. I'm aware that people have English tomorrow, and so probably aren't going to be interested in doing a live. But yeah, what can I say? I'm gonna get into some organic chemistry. So just a revision really of the stuff you need to know in organic chemistry. So I'm drawing two carbon compounds here, two organic molecules. And you can see there's a lot of bonds to draw. Okay, so drawing a lot of organic molecules. Let's get into this. So this is organic chemistry. And depending on which exam board you're doing, or whether you're doing combined or triple, then as they say, it's called triple. But yeah, depending on what you're doing, depends how much you need to know. So let's get into it. Hold on, let me just get my stuff together. Here we are. Boom. Alright, let me get into it. So I can't spell. That would help if I could spell, but there we go. Okay, chemistry exam on Tuesday, guys. So, just in case, which one of these is a hydrocarbon? So you should be able to work out which one is a hydrocarbon and why it's a hydrocarbon. A very common question. And the answer, of course, is this one here is a hydrocarbon. You might even know the name of this hydrocarbon. It's methane. But why is this a hydrocarbon? So, and the answer as to why this is a hydrocarbon is it's made of carbon and hydrogen atoms only. So really key in the answer here, a lot of people will just put it's made of hydrogen and carbon, or carbon and hydrogen, but the only is really key as well. So the other molecule which we have here is not a hydrocarbon. Why? What is there in this molecule? We got lots of hydrogen and we got lots of carbon, so but we've got an oxygen atom. So this is not a hydrocarbon. Sorry, excuse me. I've got some busted throat. Yeah, so this is not a hydrocarbon because it contains oxygen. So watch out for that in your exam. Okay, now the two main groups of hydrocarbon. Hiya, how's it going, Yoshi? Are you doing AQA? I didn't notice it was called biology cells. Yeah, I didn't notice that. I just literally flew on. Oh, yeah, why is it live stream AQA biology cells? Let me edit that. Thanks very much. We're going to change that. I just flew on and clicked whatever it came up for me. So live stream, let's do chemistry. I'm changing it now. Chemistry paper to GCSE. Okay. And let's change that. Thank you for that. I'm going to go through organic chemistry. Okay, yeah, there we go. It's changed. Thanks for that. Right, I'm back. He says, okay. So, have you heard of alkanes? These are one of the homologous series. So you'll need to know alkanes. A couple of things you need to know. What is their general formula. These are the things that are standard questions you'd need to be able to ask. What are the first 4 members of the homologous series? And a lot of people are probably revising for English, so they're not interested in this, but I'm just on here in case people want to know. Why are alkanes? Whoa. Okay, can't control myself today. Why are alkanes? If you know any of the answers, feel free to put these up in the chat. Yeah. So, nice one, guys. So, let's have a little look. General formula, well done. I can see. Yeah, awesome. Well done, ratatata. What are the first 4 members of the alkane homologous series? Do you know the names of the first 4 organic molecules? And does anyone know why they're described as saturated? Looks really blurry. I don't know why it's looking so blurry there. I don't know if you guys can see this. Can you actually see this? Or is this blurry? Because it looks really blurry on my screen. Methane, ethane, propane, butane. Okay, cool. Nice. Well done. Methane, ethane, propane, butane. So in the homologous series, the last few letters of each name tell you the homologous series. So you know they're alkanes because they all end in ane. And why are they described as saturated? Do you know why they're called saturated? It's because they're missing something. They don't have. What don't they have? They don't have a. Monkeys eat peanut butter. Yeah, nice one. That's a good share, that. So, they're saturated compounds. Yeah, they don't have a double bond. Awesome. Are you doing combined or triple, like separate science, Yoshi? Okay, cool. Then I know exactly how much to go into. As the chain length gets bigger, what physical property changes? So as we increase the chain length, what physical property changes? So for example, if I have methane, and then I go to, let's just jump up to propane, what physical property is going to change, do you think? There's a few physical properties that change with increasing chain length. So the carbon chain is 1 carbon long in methane and 3 carbons long in propane. Viscosity increases. Nice. Yeah, boiling point increases too. Good. So the answer to that, I don't even know where my hold on. Here I am. Oh yeah. Didn't even know. I'm all over the this was all last minute, so I didn't even put myself up there. Right. Viscosity increases. Boiling point increases. Yeah. However, color darkens. They get darker, basically. Color darkens. Whatever. This is crap English, but there we go. Yeah, color darkens. And flammability decreases. So Methane is more flammable and easy to light. Might make it a bit dangerous as a fuel, so we tend to use propane rather than methane. They're both gases, but propane is slightly less flammable, so it's not going to explode on you so much. Boiling point increases and viscosity increases. These are both gases, so it doesn't really count. Once you get above butane, butane is still a gas. Propane and butane are better fuels because they're not quite as flammable as methane. But once you get to pentane, hexane, heptane, which is the one with 7, then they become liquids, and then later on they become solids. So why is it why does boiling point of hydrocarbons increase with chain length? So when I say chain length, I'm really talking about the size of the molecule. So kind of goes back to paper 1. This is a little link back to paper 1. So if you think of the noble gases, as we go down the group with the noble gases, their boiling points increase. Or if you go down, the halogens is a better example, group 7. Fluorine's a gas, chlorine's a gas, then you hit bromine, which is a liquid, and then iodine's a solid. So something is changing, which is increasing the boiling point. The same answer for going down the group. Right, so it's not really bonds they're breaking. This, believe it or not, hydrocarbons are basically simple molecules. So more energy is required, absolutely. And what are we breaking? So as they get bigger, it's not bonds. Do you remember what it is with simple molecules? It's the intermolecular forces, those weak intermolecular forces. At A level, they're called van der Waals forces or London forces, but they're weak intermolecular forces. So as they get bigger, the intermolecular forces get stronger between the molecules. Well, yeah, I don't really need to write between the molecules because we've already said that. So in the very name, intermolecular forces. So I could say the forces get stronger between the molecules, or I could say the intermolecular forces get stronger. Then I don't need to say between the molecules, so I don't really need that bit. So more energy is required to overcome them, break them, whatever you want to say. Cool. Remember, you're not actually breaking when you boil something. So if I'm boiling this methane, it's already a gas, but essentially if you had solid methane, you had it at like minus 200 degrees and it was solid. If I wanted to separate these two methane molecules from each other, I'm not actually trying to break these bonds. Alkanes have actually got pretty strong covalent bonds. I'm not trying to break those. That is a strong covalent bond. If I want alkanes to react and do a chemical reaction, I'm trying to break that. But if I'm just trying to separate this one from this one in the old particle model, that's why I'm drawing a circle around them, then there's just some weak force that I need to break. Okay, so you're not actually touching the bonds. Now let me just see, because okay, coolio. Okay, let's does anyone have any questions about any of that so far? And so that's all pretty standard. Anyone got any questions about any of that organic chemistry so far on the alkanes? Let me just have a quick gander for alkanes. If you guys have to know, you got to do combustion reactions. Do you have to know? You got to know the combustion reactions. I just want to see if you're doing GCSE, you got to know the reactions with halogens, but it all depends. I don't know why this keeps losing connection, but it's a pain in the backside, to say the least. No, you don't. You don't. That's cool, yo. Right. Don't know why my connection seems bad today. I hope tomorrow when I do my proper live stream on this, it's not bad. So combustion reactions of alkanes. So who knows how to write a combustion reaction? What are my products? If I'm going to burn a hydrocarbon in oxygen, what are my products? Anyone know the two products? What two products do we always get with complete combustion? Nice, we get carbon dioxide and we're going to get water. Now, okay, it's got a little bit high. I was trying to dodge the camera there. Okay, coolio. Who's good at balancing? Let me just do the first one and show you for balancing. Because there's one carbon here, means I don't need to do anything there. I've got 4 hydrogens and I've got 2 here, so we just put a 2 here. And that makes, so really when you're doing organic chemistry, you just look at the number of carbons in the fuel you're burning in combustion reactions, and you just, that's how many carbon dioxides you need. And then you just look at the hydrogens, divide them by 2, and that's how many waters you need. So because I've got 4 hydrogens, I need 2 waters. And now it's a case of add up my oxygen. I've got 4 oxygens on this side, so I need to put a 2 here. Right, let me give you guys one of these to do. Okay. Remember, in organic chemistry, you're allowed to use halves on the oxygen, but just always balance the oxygen last. Make sure you always balance the oxygen last in combustion reactions. It's the last thing to balance. So who can tell me the balanced equation for the combustion of propane? Well, Yoshi, for combustion equations like this, which will come up in paper 2, they're really easy. You're just going to look at your propane here, C3H8, and I don't know why the server keeps mashing up, but you just go to C3 and go, well, there's 3 carbons, so that means I need 3 carbon dioxides. And then you'd look at H8 and say there's 8 H's. How many H2O's do you need if you've got 8 H's in the fuel? So these are the easiest balancing ones to do, because I've got a 3 here, so I put a 3 here. I've got an 8 here. I've got a 2 here, H2, so I need to do a multiple of 4. So we've got a 3 and a 4. Look, I've just literally transferred the 3 to the carbon dioxide and swap that over to there. Now what we need to do is add up all the oxygens. So you're going to do, well, I need to do, for oxygen, I need to do 3 times O2. What does that equal? That equals 6 O's. That looks like 60. It's a bit rubbish, isn't it? So I've got 6 oxygens there, and then I've got 4 times O. So in total, I've got 10. I've got 6 here and 4 here. So in total, I've got 10. What number do I need to put in front of O2? So what number am I putting there, guys? It's best if I move my camera less. Yeah, that's right. I need a 5. Awesome. Thank you. Well done, Sana. We need a 5 there. So put a 5 there and it's balanced. So 5 in front of the oxygen. So always with combustion reactions, balance the carbon and the hydrogen first, and then just by just putting the same number in front of carbon dioxide and the same number in front of water, and then you balance the oxygen after. I don't know what is going on with the connection today. It is rotten. Right, if you do not have enough oxygen, what dangerous gas is produced. So what dangerous gas gets produced if you don't have enough oxygen? Anyone know the name of the really dangerous gas that gets produced? Yeah, that's right, carbon monoxide. And does anyone know why that's dangerous? Probably won't come up, but it is actually also, if you're studying AQA, carbon monoxide is also in pollutants of the atmosphere. So you do need to know what the mechanism by what it does. So what does this do? Yeah, it's like suffocation, but what cells does it bind to? And it binds to something in our cells. Does anybody know what it binds to in our cells? There's a little clue here. It's toxic, you can't smell it. That's absolutely right. Very good. Yeah. Well done, Emily. It binds to hemoglobin. You can spell hemoglobin without the A. It's the American spelling. It's perfectly acceptable as well. So it binds to hemoglobin, prevents. I'm just calling hemoglobin HB, which I shouldn't do. I should write the full words. But it binds to hemoglobin, prevents hemoglobin joining with oxygen. So carbon monoxide actually, hemoglobin loves carbon monoxide more than oxygen. They have a better binding, so they attract to each other quickly, and then the oxygen can't go in, and technically Emily said you suffocate, which is absolutely right. So yeah, hemoglobin can't carry oxygen to any of your cells, not just your heart but the body cells as well, so then you can't respire and you die. You do need to know for AQA that you can fall into a coma, you can faint, or you can die, and all because of the lack of oxygen, so you can't respire. Yeah, you can't transport oxygen around your body. Anyway, that's one of the toxic gases you need to know about that's a pollutant. Right, let's take a quick look at alkenes. These are another homologous series. Homologous series of, let's just call them a homologous series. So, quick one. Does anybody know the general formula of alkenes? So something that could be just a one mark kind of question. Yep, it's CnH2n. You might be thinking, what the hell does that mean? CnH2n. This means that, well done girls, this means if the N is the number of carbons, by the way, if anybody's actually been wondering what the hell is N, it's the number of carbons. So this means that if C is 2, you just, to find out the number of H's, you just go 2 times N, so you just double it. And there you have the first alkene. And this C3, H8, no, H6. Does anyone know the name of these first 4 alkenes? Or first 3 alkenes? We'll just do the first 3. And then you need to know why alkenes are really useful as well. So no, you don't need to know that. All depends which. Yeah, there is no methane. Why is there no methane? Now there's no such thing as methane. The first alkene is actually ethene. Why can't we have, we can have methane. Why can't we have methane? What's the rule with alkenes? So alkenes, and I'll just write it here. Alkenes, I can't even spell. Alkenes are unsaturated. Alkenes are unsaturated. What does this mean? I don't know why my internet keeps going on a bogus thing. Alkenes are unsaturated. What does that mean, guys? Don't know why I got double question marks. Double bond. Awesome. Now, just to ensure you definitely get the mark, it's much better to say carbon, carbon, double bond than just double bond. There are other double bonds that doesn't make something unsaturated. So they have a carbon-carbon double bond. If you want to make sure, you can just write the double, you can just C equals C like that. Yeah, they got a double bond. Okay, so think about methane. If there was such thing as methane, meth means one, so one carbon. Look, I can't have a double bond because I can't have a carbon-carbon double bond. So the first alkene has to have two carbons, so the first one is eth, which means two. So pro means 3, but means 4. So pent means 5, hex is 6, like a hexagon, and then you have heptane, but you don't need to know all that, heptene. Okay, I don't know why it asked. This thing keeps connecting. I feel like hotspotting off my phone, but there we go. Don't know what's wrong with my internet. BT have been mashing me up just from yesterday, which is not good. I need to get that sorted. Right, couple of other things then. What are alkenes? Why are alkenes in demand? Why do you think alkenes are in demand? Jeez. Anyone know why alkenes are in demand? There's two things we can make from alkenes. Yeah, they're more reactive, so there's two reactions. We can get two things from alkenes, which you do later on in organic chemistry. They are more flammable. However, they don't burn. They're not as good fuels as the small alkanes. They burn with a smoky flame, so they're actually a bit rubbish to burn. And the reason why they burn with a smoky flame is if you look at the ratio of carbons to hydrogens, there's, say we look at butene, there's 4 carbons, 8 hydrogens. You get more particulates with alkenes. Whereas if I was to burn C3H8, you've got over double hydrogen. So there's a higher carbon to hydrogen ratio, so they're actually not so great as fuel. It's actually because, so the answers are, they can be turned into polymers, which is plastics. So everything in your house that's plastic has been made from an alkene. They can be turned into alcohol. So if you're looking at like alcohol that's in hand wipe, like when you're disinfecting your hands and stuff, that is, yeah, they're good solvents. So like alcohols. Yeah, that's right. They make alcohols and they also make plastic. So they're the two main reasons why we want alkenes. Okay, is there anything straight off the chain that you need to know with alkenes? See, it's so weird because if you guys are doing, I just have to check, because if you're doing combined now, you don't have to really know a lot about alkenes. Okay, you guys have got to know a bit more about alkenes, so let's get down to alkenes. If you're doing triple, you've got to know a little bit more about alkenes. So alkenes burn with a smoky flame as they have a higher carbon to hydrogen ratio. There's more carbon atoms per molecule in a molecule of alkenes, so you get the black sooty flame, which isn't so good. Alkenes undergo addition reactions. So addition reactions are when things add on. So they undergo addition reactions. We'll have a little look. This is a very classic addition reaction. You know what, the issue, I don't know why it keeps mashing up at the moment, but so if you look here, this is ethene. Does anyone know? Okay. Anyone know what this makes? You have ethene. You've got bromine. What does this make, guys? Yeah, doing a little bit of triple here. So this a little just gone into dipped into a little bit of triple. This is a little bit of triple. So this is the test for alkenes, and it makes dibromoethane. Yeah. So what happens is, because the double bond disappears, and a bromine molecule joins. So I put mine at the end. I could have put them at the ends, but I'm being a bit lazy. But essentially, the double bond, the bromine adds to the double bond. So a couple of ways to check if it's addition. If you have a double bond, it's always going to be addition. So dibromoethane, it's now become ethane rather than ethene. Di meaning two bromines, so that's dibromoethane. Yeah, nice one. Yeah, orange to colorless. I'll go over the ratio bit. Nice one. Thanks for that question. That's a good one. Orange, and then this goes colorless. This is actually the test for a double bond. Now, it's not just alkenes that have a double bond. They can give you questions about unsaturated fats. Olive oil, avocado oil, coconut oil, all these really healthy oils are unsaturated. They have double bonds, and you can find out which one is the healthiest, which one has the most double bonds, by adding bromine. And once all the bromine's added, it will go orange or whatever. So you can see how many you can add until it goes orange, how many drops of bromine. So if I was comparing coconut oil to olive oil might take more drops of bromine to add until it turns orange, because there's more double bonds. So it depends on how many double bonds. Anyway, that's just something in a context they could put. Right, someone asked a question about the ratio bit. Let me zing to the ratio bit. Right, let's go back here. Oh no, let's go on. We've got plenty of space. Right. So, yeah. You're absolutely right. If you look at the general formula. So if we look at, let's take ethane. Right. What's the formula of ethane, the alkane? Formula is 2 carbon, 6 hydrogen. So when I burn that, the oxygen is more likely to form water than carbon monoxide or solid carbon. When you burn ethene, the alkene, you're more likely, you get more unburnt carbon left over, which is soot, and you get a black smoky flame. So it's just the chances of you having a sooty black flame is higher with alkenes, because the ratio is 1 to 2 in alkenes, but it's greater than 1 to 2 in alkanes. There's 2 carbons to 6 hydrogens, so it's times 2 plus 2. So the ratio, there's slightly more hydrogen. Let's have a little look. Oh yeah, thanks for that, Ibrahim. Now, what else? Yeah, so there's also a reaction called hydrogenation, guys. If you're doing triple, this is really for triple kids, this bit. And then I'm going to go on to fractional distillation, which is for everybody. So this is called hydrogenation, or you can actually just call it hydrogenation. Some people pronounce it hydrogenation. And this is turning an alkene, like ethene. What would I make here? Again, it's another addition reaction when we're opening up the double bond and we're adding across it. How do you know you're doing addition? You'll go from 2 things to 1 thing. So I'm only going to make 1 product because you're sticking 2 things together. So what do you think I'm going to make here, guys? It's not going to be dibromoethane. What's it going to be? Nice one, guys. Oh, look at these awesome people, man. They know the catalysts and the pressure as well. Yeah, so you're going to make ethane. You need a catalyst. Let me just check. Do you need to know for AQA? Do you need to know the pressure bit and that? It just says catalyst. I don't know whether you've got to know the pressure and... Yeah. Catalyst, 300 degrees, 70 atmosphere. Phosphoric acid as a catalyst. Okay, yeah. Some people used to say a nickel catalyst could be used. What else have we got? Yeah. We'll look at the higher calculations. Okay, let's check out fractional distillation quickly. They love to ask questions on this. So here, if you've just struck oil, remember all hydrocarbons come from crude oil. Crude oil is a fossil fuel made from the dead bodies, mainly of marine animals, those little things whales eat called plankton. They fall to the bottom of the sea. 100 million years later, pressure, heat creates crude oil. So they're non-renewable and they're running out. If you're lucky enough to discover a massive lake of oil under the land you own, you're now super rich. Like the Texans or the Arabs, some of the Arabs in the Middle East, or some of the Russians, or anyone who has found a lot of oil. Now, the problem is all crude oil is not the same. So some crude oil, this is combined as well. What I'm doing now, this fractional distillation, is also on combined. So, excuse me, some of it is combined, some of it is triple. So I'll point out when it's something triple, so you don't need to pay attention. And basically, fractional distillation is a nice 4 or 5 marker, so can come up. All good, guys, all good, don't worry about it. So crude oil enters here into the fractional distillation tower. There's 5 things you've got to say. It's basically, how do we separate crude oil into useful stuff? If you try and burn crude oil, it doesn't burn easily. It's not a very good fuel. It's not very useful on its own. But if we separate it, we can end up getting lots of different fractions, and we can get fuels, we can get stuff to make the roads, we can get fuel for aeroplanes, we can make plastics from some of the products. So there's loads of things we can do. So straight out the bottom, without at all vaporizing, we have bitumen. This comes off, and this is used on the roads, so you just need to know bitumen is for roads. And then you've got 5 more things. Now, depending on which book you look in, literally, if I go from GCSE to AQA to OCR, they all call each fraction different things, which is a bit annoying, but there we go. In the exam, it wouldn't matter if you called them something outside of your spec, it would still be correct. If it's correct, it's correct. So then you've got kerosene, then you've got petrol, and then you've got natural gas, or in AQA they call it LPG, liquefied petroleum gasoline, but you can call it refinery gases or natural gases. So, okay, nice. Right, here we go. Do they separate into molecules with different chain lengths and boiling points? Absolutely. Spot on, Yoshi. The different boiling points decides where they leave the fractionating column. Boom. Awesome, midget. That's awesome. This is for AQA. Yes, it absolutely is, but this applies to everything. So if I was asked for 4 or 5 marks, fractional distillation is in every exam board, but it does depend. In certain exam boards, you may have already done fractional distillation in paper 1, so then you wouldn't be so interested in this stream today. So step 1, this is the first mark. If you're asked, now they can be quite clever. They might say, ooh, how'd you carry out fractional distillation of crude oil? That's basic. Sometimes they'll say, how'd you separate petrol and kerosene? Or how'd you separate heavy fuel and diesel? Lovely people, kill that horrid boy. That's nice. Good. So what you want to do, okay, number 1, vaporize the crude oil. You will get the marks if you say heat or evaporate. Okay, don't know why it's all in capitals, because vaporize the crude oil. 2, somewhere in your answer you want to mention the tower has a temperature gradient. Literally, you will get the marks if you say the tower is hot at the bottom, cold at the top. But you can say temperature gradient. You can call it a tower or a column. Again, that's totally up to you. So it's hot at the bottom, it's cold at the top. This is like a 5 marker, 4-5 marker. Yeah. I will be doing a live stream for chemistry as well tomorrow. Yeah, defo. But I wanted to get a little bit out of the way just in case, because sometimes I might not be able to get through it all. So I don't know what vaporide is. That's some new way of saying vaporize. So vaporize the crude oil. The tower has a temperature gradient, and then what we want to say is fractions rise up the tower. You can call it a column, fractionating column, or a fractionating tower. Fractions rise up the tower, and then you guys said the rest of it nicely. Okay, yeah, Midget, I'll get onto that. But you said it perfectly. So even if you're like confused, the great thing is, even if you're confused, Midget, you've actually got the knowledge there to get the full marks, because you don't have to understand it, but I will explain it. So exactly what you said, higher boiling points. Now you just have to say different boiling points, different fractions. Let's just say we just say keyword different fractions. You can say hydrocarbons, you don't need to say fractions, but different fractions condense at different heights, parts of the tower, sections, it's up to you, depending on their boiling points. So depending on their boiling points, they condense at different points. And as Midget YT said earlier, and Yoshi, higher fractions with higher BPT. By the way, I'm saying fractions. You can say molecules, hydrocarbons, compounds. It's up to you. I'm just using the word fractions. So fractions with higher BPT condense lower down the tower. And then going back to what we learned before, if you're ever asked why do some fractions have higher boiling points, it's because they're larger and they have stronger intermolecular forces. Now, somebody asked, why do the higher boiling point ones come out of the bottom? It don't really make sense. Well, let's look at the temperatures. So let's pretend let's pretend that's 500 degrees. And let's pretend up here this is 30 degrees, right? So let's pretend these are the temperatures, 530. When you come in at 500, think about like bitumen boils at 550. So bitumen turns to a gas at 550. So bitumen doesn't even turn to a gas. It just comes straight out the tower as a liquid. Let's say heavy oil boils at 490. So heavy oil turns into a gas at 490. So straight in the tower, heavy oil here in blue has turned into a gas. But as it rises up the tower and it gets to say below 490, let's say it gets to 450, it loses its energy that needed to keep the molecules apart and break the forces. The forces reform, it condenses and comes off. So essentially, higher boiling points turn back to liquid first because they're more stable as liquids. Things that are smaller molecules are more stable as gases, and to get them to be a liquid, they don't need a lot of energy to become a gas, basically. So yeah, if you had water here, water would still have 100-degree. Water wouldn't come off until you went below 100 degrees. So you'd have to go further up the tower than 100 degrees. You'd have to get to like 99 degrees and then the water would come off. But yeah, you don't have to explain that. So it's nice to understand it, but you're at the stage where you got your exam on Tuesday and it's just like, let me get those facts down so I can do it. Yeah. So fractional distillation is really important if you've got the oil. What do you do if you're mega rich, you want to buy your palace, your castle, whatever, and you find out that the oil that you own, the oil in your country, is all crappy bitumen? Yeah, that's great for selling to people to put on roads, but which of these are going to make you the most money? Well, what does everyone in the country have? How many cars are there just in England? There's 50 million cars in England. Some people own 2 cars. Some people own 3 cars. Now, there's a billion people in China. Half of them have cars. That's 500 million cars. There's a billion people living in India. If half of those people own a car, that's another 500 million cars. So you really want to be in the business of selling petrol, and you're going to be so rich you could literally go use money as toilet paper, basically. So what do? Absolutely, Emily, if you've been unlucky enough to get bitumen and heavy fuel oil for big container ships, and you're like, damn, I want those small alkanes or alkenes, which I can make alcohol and plastic out of, then you need to do cracking. So let's have a look at cracking. Cracking turns large hydrocarbons, I don't know, large alkanes. What does it turn them into, guys? If we crack a large hydrocarbon, what does it turn them into? Anyone know on the chat? Let's say I've got, I don't know, I've got dodecane, C12. If it's an alkane, what would be dodecane's formula? C12H, think CnH2n plus 2. Great, I get a shorter alkane and an alkene. Yeah, short chain hydrocarbon, and you'll always get an alkene. When you crack an alkane, you have to get an alkene because there's going to be an end with no hydrogen, so a double bond forms. Absolutely. How many hydrogens would dodecane have here? 26. Nice. Times 2, add 2. Great. So now, this is up to you. Watch out for this. They can pull a sly one. You're going to 100% make an alkene. So you'll definitely get an alkene like C2H4, but just watch out. They might do some. I've seen them do really disgusting things like this. Put a big multiplier there. That means we've got 3 of those, and they're going to say to you, what is the other molecule? So guys, what is my missing alkane? You're always going to make an alkene and an alkane. What's my missing alkane? So I'm going to have C6 left over. Can't be H22. Look at the big red 3. That's a multiplier for everything after it. If I've got 3 ethene molecules, I've got 3 lots of C2H4. So what's the H? You're right with the 6, by the way. C6H14, that's it. So just remember, when you're balancing or when you're writing equations, the multiplier applies to everything in the molecule after it. Yeah, you got it, C6H14. And that would be known, you don't need to know, this is not on your syllabus, but that would be hexane, okay, which is an alkane. So hexane is going to be more useful than dodecane. Dodecane, which is the C12, isn't going to burn anywhere near as well as hexane. Hexane's a better fuel. Why are alkenes? So what we need to say, we need to ask a question. Why are short chain alkanes more in demand? And why are alkenes in demand? You might even be asked about why do cracking, and it's a supply and demand issue. So, but why are they more in demand? Yeah, C2H4 is one molecule. Yeah. Why are they more in demand, short chain alkanes and alkenes? Server 503, whatever the hell that is. Yeah. Good. Yep. But that's not for the alkenes, remember? Because the alkenes make smoky black smoke, so they're not as useful. More useful fuels, basically, short. I wrote that a bit wrong, but short alkanes are more useful fuels. And then alkenes are monomers. What's a monomer? Anybody remember what a monomer is? What's a monomer? Yeah. It can be turned into, so alkenes are monomers, can be made into polymers, big molecules, or whoops, alcohols. Yeah, cool. And remember, alcohols are solvents and stuff. Right. Yeah, that's right. That's right. You do need to know. Okay, you guys have got to know some of the conditions for cracking. And if you're combined or you're doing triple, you have to know this. So it's combined and triple have to know this. What are the conditions for cracking? Yep. High tech. Right. Yeah. There's kind of thermolytic cracking, catalytic cracking. Yeah. Steam cracking and catalytic cracking. So catalyst. So what we do is vaporize the large alkane and pass over an aluminium oxide catalyst. Now, there's about 4 names for this catalyst, okay? So you can just say aluminium oxide. Some people call it alumina, A-L-U-M-I-N-A. You can also use silicon dioxide or silica, it's known as. So there's like 4 different ways of, you can write the formula, but basically you turn the dodecane, the C12H26, into a gas, and then you pass it over the catalyst and it will crack, and that is known as catalytic cracking. And then there's also something called steam cracking, where you just heat them to an incredibly high temperature with steam. So yeah, you mix it with steam and heat it to a high temperature. This is AQA, yeah. The 450 degrees and 200 atmosphere, that's your Haber process there. With an iron catalyst for the Haber process or Haber process. Yeah, so your Haber process, 450 degrees, 200 atmospheres, and of course, an iron catalyst, Fe. Um, Cool. Yeah, if people have had enough of organic, I can. Which one's topic 10? What's topic 10? Is that chemical analysis? What is? Condensation polymers. Yeah. I could go over condensation polymers. Let's go over condensation polymers. Yeah. So, all depends really on which exam board you do. GCSE and AQA love a bit of condensation. Let me just show you recap addition polymers first, for those of you that can't remember addition polymers. So addition polymerization will take 2 secondos. So this is ethene. I need to show you the big the thing they do a lot, which is catches people out with addition polymerization. So addition polymerization is where I'm going to take a load of monomers. The N can be any number, so it could be a million, and we just want to write N as like an algebraic form. I'm going to join that million together, and I'm going to copy this out exactly as over on the left. So if you're asked to draw the polymer and they give you the monomer, copy it out exactly. Your 1 mark is for leaving the ends open, putting a bracket through them like that. Now you can then put an N there to say this goes on forever. They might ask you to draw 2 units, in which case you've got to draw 2 repeating units. So in that case, I'm just going to do the same thing again. Now here's this one's really easy. Just leave the ends open. Make sure with a polymer you don't close the ends. Now, this can be tricky for some people. It's natural to think the double bond has gone. So because the double bond has disappeared, it's no longer an alkene, it's an alkane. But we still give it the name of the alkene. We say poly, meaning many, and then ethene. So it's really telling you what it came from. It's giving you its like what it came from. It's saying polyethene, many ethenes is what it came from. So you don't change the name there to ane like you might suspect. That's known as addition polymerization. Okay. And no. I'll show you what a double bond is. Okay. I'll show you what the double bond is. So each black line is a pair of shared electrons. So a dot and a cross overlapping. When you have a double bond, it means there's two pairs of shared electrons. I'm just going to show you very quickly because of that question. Let me just show you. So, just because of that question, I'm just going to show you this, right? And then I'm going to go to one more addition. I just need to show you the trick. The polypropene is, you really got to watch out for that, but I'm just going to show you this. So remember what we're doing here. These are just models. Remember, they're just models. But why do we have a double bond? So all this means is that why is that single? Because hydrogen is sharing its lonely little electron with one of carbons. So there's two electrons there. But if we come, so each one of these is a single bond because there's a pair of shared electrons, and the definition of a covalent bond is a pair of shared electrons between two nuclei. Now, if we go to the middle, there's actually 4 electrons. There's 2 shared pairs, and that's why you have a double bond. And if you have nitrogen, which has 3 bonds, called a triple bond. There's no such thing as a quadruple bond in the whole of chemistry. Triple is the most bonds you can have. So if you have a triple bond, that's 3 pairs of shared electrons, 3 crosses, 3 circles. So that's where the double bond comes from. Now, the tricky addition polymerization I want to show you. I think I'm going to do one. I'm going to try and do one at 8. And I just want to show you the tricky. Watch out for this. This is a tricky addition polymerization. And then I've had a thing to do condensation. And then I can do a bit of chemical analysis. But I'm probably going to do some of that tomorrow. So what the hell is that? Right. Watch out for this, guys. This one is brutal if they give you this. So this appears all straightforward, right? This is where students mash up their exam if you get propene. If they give you this, and they've done this hundreds of times, they give you propene and say draw the polymer, everyone gets confused and they're like, oh, by the way, I've made an error there. Can anyone spot my mistake in propene? I made an error with propene. Where's my screw up? Anyone spot my accidental mistake that I'll claim is on purpose in my structure of propene? How do I know that I've not drawn propene right? Yeah, right here, carbon is in group 4 of the periodic table. It can only have 4 black lines around it because it only can share 4 electrons. So I need to rub that out. Nice. Yeah. I need to rub that out. Right. Get rid of that cruddy red line. Okay. So carbons in group 4, just count them up when you're drawing alkenes, because it's easy to do that when you're drawing the structure. Okay, here's where people screw up. They come over here and they're like, oh, I need to take away the double bond. Then they're like, I'll stick this carbon here. Oh, what am I doing? They start to get really confused, right? Where do you leave the open end and where do you put the bracket? Secret is you've got to turn that. See, I've got this space here. You see there's an empty space here. I need to rotate that carbon with the 3 H's down here. So I need to put this down below. So if you get propene, tuck that down below. I can write it as CH3, or if you really want, you can put all the hydrogens out. I can just put CH3. Then put your line up here, and then the line there and there, and the brackets. So watch out for that. If you get propene, you really need to tuck everything underneath or above, wherever the space is. Tuck it round and leave a line going across, and just put an N, meaning going on for like ever kind of thing. So yeah. So watch out for that. And this would be called not polypropane, but polypropene. So do people want me to no, it doesn't matter where you put, it doesn't matter where you arrange the CH3. You could like, so all that we've done is we've tucked that CH3 underneath there and then left the line. You always have to leave it open, because with the double bond, you'd want to join another one on. You can't join another one on here. This is taken. The only place we can join one on is if we tuck that down, open out the double bond, then I can join another propene and another one and another one. So watch out for that. You have to leave the ends open with addition, polymerization. What did people want to go through? I've seen someone said Le Chatelier's principle. If you've got that coming up tomorrow, I don't know if everyone has that coming up. Sorry, on Tuesday. Condensation, amino acids and DNA. All right, let's have a look at condensation polymerization. This might not be for all of you because you've got to be doing triple for this. So let me just do condensation. So with condensation polymerization, what does condensation make you think of? So you got to think, what does condensation actually make you think of? Water. Yeah, water. Absolutely. Spot on. So with condensation, are you using water, putting it in, or is it coming out? So if I said, oh, there's some condensation, have I used the water? Is water coming out of something and appearing somewhere? Basically, kind of a bit of a stupid question, but water's appearing. So water's coming out, and where the water comes out off of the bonds, that's where the two molecules join. So this isn't addition where they have a double bond. This is taking away water from the atoms, and where the O and the H's were, you draw a line. And so we're going to look at that. Let's have a look. Now, they don't want you to waste time drawing all the big long carbon chains because it's a bit annoying. But boy, it is hot today. Jeez. Okay, so look. Essentially, what I want to show you here, now depending on what exam board you're doing, they call these different names, but notice what's unusual. What type of molecule have I just drawn? Does anyone know? Does anyone know what I've just drawn? Yeah, I do physics as well, so I'll be doing the physics as well, but I'm not doing that today. Yeah, so yeah, this is condensation. Oh no, and when an ester's formed, it's not. It's okay. When an ester's formed, midget, YT, it is a condensation reaction. We take one water molecule out. But it's not polymerization, because with a normal carboxylic acid and alcohol, you only have a functional group at one end. When you have double functional groups, it's an alcohol, but this is a special alcohol. It's not ethanol. Close, guys. It's got the OH and it's got 2 carbons. This is a diol. You can, for your examples, just call it a diol. It just means there's 2 alcohols, one at each end, 2 hydroxide molecules, which in organic chemistry are known as alcohols, alcohol functional groups. Now, the exam board don't want you to get bogged down drawing all the carbons and hydrogens in between. So if you're doing AQA or you're doing any of the exam boards, they have a shorthand. They say don't bother with all of that, guys. Just understand that that there are carbons and hydrogens in the middle. They don't want you getting bogged down with all that. So they're saying we're going to draw a rectangle in the middle. You don't need to colour it in. But essentially, that's all the carbons and hydrogens. So this could be ethan diol, meaning 2 carbons with an OH at each end. This could be butan diol, 4 carbons in the middle, OH, OH. Can be either. Now, we're going to react this. We're going to react this with, and if it's polymerization, I put an N there to say I could have a million of these diols, and I'm going to react this with a dioic acid. Now, for some reason, you can call them dioic acid, but for some reason now this time, guys, I could have 3 carbons, 4 carbons, it doesn't really matter. Here are, does anyone know what I've just drawn just now? What's this molecule that I've just drawn? What type of molecule have I just drawn here on the right? Yeah. Oh, Sana, it is like ethanol, but it has 2 OH groups. So it's ethan diol. Yeah, carboxylic acid, but this is a strange one. You can call this dioic acid or dicarboxylic acid. Now in AQA in the CGP, just had a sneaky look, they call it dicarboxylic acid. You can actually shorten it to dioic acid. But let's go with what they're saying, dicarboxylic acid. So we join these 2 together, okay, and yeah, perfect, Phantom, dicarboxylic acid. Right, now someone asked me about is it when you join an ester and a carboxylic acid and you just make a standard ester, is that condensation? Yes, but not condensation, polymerization. If I only had one group here and one group here, I can just join once. I can't make a big chain. I can join these to make an ester, but I can't make a big long chain. But because I have another one there, I can get another OH and we can go on forever, just joining. That's where it becomes polymerization, okay? So this is condensation, polymerization. But when ester and carboxylic acid join, a water molecule comes off. We call that condensation as well, but you don't need to worry too much about that. Right, guys, these are the atoms that are going to come off. A hydrogen comes off from the alcohol, and the OH goes from here. So all you've got to do is rejoin those back together to make the polymer, and then the difficult bit is leaving the ends out. The difficult bit is drawing what this molecule looks like. You have to remove 2. Here's the hard bit. I've also got to cut off this, and I've also got to cut off this. So when you want to do it, you've got to cut the H's off of the alcohol and the OH's off of the carboxylic acid, and then redraw it. So let's redraw this, guys. So a bit long, I know, but this is just to show you. I've got an O there. I'm going to go boom, bracket. Then I've got an O here. We've lost our H's, remember, on our alcohols. I'm going to go straight across, draw the C, double bond O, rectangle. Remember, I lost an OH at the bottom, and then here, double bond C, O, and you can just do it like that. So, or if I want, you can stick the O there. As long as you've got enough O's and that, it doesn't really matter. Some people leave an O there and they cut an O off here. It doesn't really matter. As long as you've shown 2 water molecules have come off, it doesn't matter. So 2 water molecules came off. Okay, 1 water molecule came off in the middle, and then half at one end, half at the other end, so they can keep joining forever like that. So it's a bit annoying, but that's condensation polymerization. Okay, and this is a polyester. So you've probably got lots of things in your house that are polyester. In your school uniform will be polyester. In a lot of your clothes will be polyester. So yeah, right. Yeah, yes, Lloyd. You got to take the H off of the alcohol and the OH from the carboxylic acid. But technically, would you really know? No, you wouldn't. Like when you join it all back up, it doesn't really matter as long as you end up with the end result right. And let's just make sure you've removed, when you count it up, just make sure you can count, like I've removed 4 H's and 2 O's. Just make sure you've removed 4 H's and 2 O's. But technically, if you wanted to know, the OH comes from the carboxylic acid and the H from the alcohol. So, coolio. Right. DNA is also another version of a condensation polymer, and so are proteins, because amino acids have a carboxylic acid and an OH group at either end. To do all of this would be at least 3 marks. So you get error carried forward and stuff, and even just showing the waters coming off. A lot of people will do it and then forget to write the 2H2O, or they'll forget the 2H2O. This is AQA triple. This is yeah, so you just need to make sure you cut off 1 H from one side and an OH to make a water molecule. So an OH from one and an H from another. Let me do another one with you so you can see there's another version. I mean, again, this, you do all this revision and then they don't even ask any of it, and it can be annoying as hell, right? You do need to know, if you're doing triple, you need to know about amino acids joining together. You all know amino acids form proteins on the ribosome in protein synthesis, and so this is an amino acid. Why is it called amino acid? It has NH2, which is an amine group, and then it has the carboxylic acid from chemistry at the other end there. So what we have here, I've got OH and I've got H. This gives this molecule, even though it's not identical on both sides, it gives the ability to do condensation reaction. Anytime you see H's and OH's, things can do a condensation reaction where you take away water and you join them together. So what I'm going to do, what would this look like if I had another one? Well, simply this and this are going to get together, break off, and then you're just going to draw a line joining the other bit up, okay? So this is 2 amino acids forming a dipeptide. But when you do this, what you've got to be aware of is you also must show the examiner you understand that this is going on forever. That not forever, but there could be 1,000 amino acids in a protein. So I need to show him or her that I mustn't leave it intact at the ends. I mustn't leave it intact. I need to remove like 1 hydrogen here and an OH here, and then leave the lines and put the brackets to say, look, I know this is going on and on and on. So that's what you would do. You can write the OH together, or you can write it showing all the bonds, like bond O, bond H. Either's good. This is triple AQA so far. Yeah. This is another one of those things that could well not come up, guys. You could like revise this till the cows come home. What you want to do is make sure, so right, every time they get you to do condensation reaction, you're going to remove two water molecules. You have to remove the one in the middle and then one from the ends. You'd say, but sir, isn't it one from each end? Yeah, in total, remember, there's going to be, on this side, there's going to be an OH that this bad boy joins with. We don't need to show that. And over here, there's going to be an H from another amino acid hanging out here, right? There's another one off the page. There's another, like, carboxylic acid end to the other amino acid. We don't need to show all that. So we just need to show that we are aware that the reaction is occurring at both in the middle to join the two together, but then at the end so that others can join on. We need to show that. So it's always 2H2O in condensation polymerization, always 2H2O. If you're just doing like an ester, a carboxylic acid, and one alcohol, then it's just going to be one water molecule, but then that's not polymerization. So I can go through that water treatment. Hold on, let me just, so it was mainly organic. So if I was redrawing this, I now put my double bonds vertically up. I draw a line across to the nitrogen. You can put the hydrogens any side you want, by the way. They're not taking marks off and saying, oh, you put the hydrogen above or below. That's coming off the nitrogen. You don't need to do that. Now a CO. And then I just need to make sure that I've only removed two H2Os. As long as I've only removed two H2Os, we're laughing. Yeah. And then 2H2O. But if you want, you can put N here, because I don't know how many. You can just write N, because this could be 1,000 amino acids in this polymer. Then that would, N would be 1,000 waters coming off. So yeah. Oh, that don't help. Oh yeah, we did fractional distillation. 2H2O. Nah, not necessarily. Like say I go here. In polymerization, it's always going to be 2, but you can just leave it as N unless they say how many water molecules come off. You can just leave it as N sometimes rather than writing 2H2O. You can write 2NH2O. So you can say, like, I'm aware that it's going to be 2 depending on how many of these how many monomers there are in the polymer. So you can do it as 2NH2O. But yeah, it's if there's only two things joining together, it would be one water molecule. Yeah, I did fractional distillation. Whoopsie. What's topic 8? Flame tests. You just got to know 5. So chemical analysis. Okay. Well, flame tests identify positive metal ions, and there's 5 you need to know. So who's going to tell me the colors? Who knows the color that lithium goes if a lithium ion hits a flame? You need to know the colors of these ones. Okay. And let me just check. Yeah. You only need to know these 5 colors. Sodium's yellow, potassium's lilac, calcium is brick red or orange, lithium is crimson, well done, and copper is blue-green. Yeah, blue or green for copper, you get a choice of two. Great. Now, think about it. These ions, you cannot have lithium ions on their own in a solution. You cannot have sodium ions on their own. It doesn't exist. They do not exist in this form on their own. A positive ion always needs a negative ion. There's no such thing as a solution of lithium ions. So you will need to identify the positive ion. You could get a long ass question on identifying something. You need to carry out flame tests to identify the metal ion, and these are the flame tests for metal ions. They're going to give you the positive metal ion. Some metal ions don't have a colored flame, so we have another way by precipitation. Now, precipitation tests will allow you to identify some other ones. So, does anyone know the chemical we add in a precipitation test? I'll go over the chloride test in a sec. So, if they ask for the... Oh my days, check out the precipitation. I can't spell precipitation. So, for precipitation, yeah, nice one. You're going to add NaOH, and that is AQ, which is just shorthand for writing solution. Sodium hydroxide. So you're going to add sodium hydroxide, and you're going to get certain colors. And you might say, but hold on, I've already done a flame test. Why the hell do I need to do add the sodium hydroxide and do this? Well, I'll come on to that. So they like to test you out, and say you've got a white precipitate, and then you can say I can separate them with a flame. So check this. Think to yourself, why are they telling me there is two with a white precipitate? What's the point in that? Because what they're going to ask you, if this comes up, they're going to be sneaky and say, okay, calcium or whatever, your solution X and solution Y both give a white precipitate with sodium hydroxide. How can we tell the difference? We carry out a flame test. If we get an orange color, it's calcium. So orange is calcium. So you can use the flame tests and the precipitate tests to distinguish. Whoops, potassium. I write purple. You can just say lilac, but I write purple because P for potassium, but yeah, it all gets a bit confusing. Why am I writing sodium? This is yellow, and this one is crimson. Magnesium will just gives off a white flame, but magnesium ions don't. They won't burn with any, I don't think they burn with any flame in particular. So if you wanted to tell the difference, you'd go, right, burn them both in a flame test. If either of them gives off an orange flame, it's calcium ions that I'm dealing with. So watch out for that. There's other ones in these. There's other ones you need to know, like iron 2+ is green, and Fe3+ is brown, red. Listen, they can be really specific as well. If they say what is responsible for the white color, the white solid, don't say calcium 2+ ions. If they say what is responsible for the green precipitate, don't say Fe2+. The green precipitate is going to be FeOH2, and that is a solid because it's a precipitate. So it's iron hydroxide, iron 2 hydroxide, that's giving you the green color, but it was caused by the Fe2+. So there's a whole bunch of these colors. I don't want to go through all of them because they're already in your these are already in your like your CGPs and that. But basically it's more the principle you need to get, that once you've identified the positive ion, you have to identify a negative ion. Okay, so you need to identify the negative ions as well. And you've got halides and you've got the halides, you test for these by adding silver nitrate solution, and you have to know to add dilute nitric acid. So you've got to add silver nitrate and dilute nitric acid, and then you have to know the colours that these go. These will give out a precipitate as well. So you're going to get AgCl, white, yellow, cream. Nice, nice. I think of it as off milk. Like milk going off. And that's going to be cream. And then you've got AgI is yellow. And that's a solid. Remember, precipitates are solids. By the way, if you see a chemical reaction and it says, what would you observe? If you see a solid on the product side, you say, I see a precipitate or I see a solid form. Sometimes they just ask you something they have to ask you. They probably already asked you in paper 1, but here's a reaction, state 3 things or 2 things you would observe in the reaction. If there was a solid in the reactants and it's no longer in the products, the solid has dissolved or disappeared, you'll get the mark. If a solid has appeared in the products and there was none in the reactants, then you say a precipitate or a solid has formed. So you've got to make sure you look at state symbols in order to be able to describe what you can observe in a reaction. Yeah, they probably asked that in P1 already. Right, so for example, I now know if I get a crimson flame color, I've got lithium ions, and then if I carry out the halide test by adding silver nitrate and nitric acid and it goes white precipitate, I know I've got lithium chloride was my original compound, LiCl. If I get a cream precipitate, then I had lithium bromide. So the flame test or the sodium hydroxide precipitate test give you the metal that's part of the ionic compound you're looking at in these tests. By the way, yeah, so halides, cool. There's also sulfate ions. Anyone know the test for sulfate ions? You have to know the test for these as well. Pretty disgusting, but there's a test for this. So this is going to tell you, let's say you had a red flame, which would tell you that you had lithium. Then you do your negative ion tests, your anion tests, and this is going to tell you, yeah, white precipitate, hydrochloric acid and barium chloride. So you're going to add, you always add an acid to remove impurities. And when they're talking about impurities, they mean carbonates. Acids will erode carbonates. They'll form carbon dioxide and they'll get rid of the impurity. So add hydrochloric acid and BaCl2, barium chloride. Oh my days. And you're going to add barium chloride solution. Now barium chloride, like most chlorides, is soluble. It's AQ. Okay, so most chlorides are soluble. Barium chloride, I think only lead chloride isn't soluble, but there might be a couple of others that I'm missing. But barium chloride is soluble. When the barium reacts with the sulfate, you get a barium sulfate solid precipitate. As people have said, that is white. So this is quite long, but you probably don't really need me to go through all of these, to be honest with you. Yeah, the newbie block, I just did amino acids, so you can have a look at that. That's about like 5 minutes back or 10 minutes back. Yeah, this is a bit of AQA triple at the moment here. Yeah, white precipitate barium chloride. Yeah, chlorine does. Lloyd, you were asking about chlorine bleaches damp litmus paper. If they ask you for a test, so Lloyd made a really good question, by the way. Lloyd asked a really good question. So if they ask you about chlorine gas, or they ask you about chloride ions. They are two different things. Ions are always in solution. So no, you can't test for chloride ions with the damp litmus paper. This is the silver nitrate test with HCl. You cannot use these tests interchangeably. They are separate tests. Chlorine gas is something different. Chlorine gas is two covalently bonded chlorine atoms. Chloride ion is one atom with an extra electron in a solution, so it's something different. And this is the damp litmus paper. So check out what they're asking you for. If they say, what's the test for chloride ions? Silver nitrate, hydrochloric acid. If they tell you, what's the test for chlorine? Damp litmus turns red, then bleaches white. So they're two different things and two different tests. So watch out for that. They're not the same thing. Finally, if you need to test for carbonates, CO3 2-, if you need to test for these ions, which is the carbonate ion, just add acid. They're going to give off carbon dioxide, and then you can use lime water. So you can pick an acid really. I'm going to go with hydrochloric acid just because that's the one they mostly say. But add hydrochloric acid, test for present. Oh gosh, let's forget the spelling of carbon dioxide with lime water. Whoa. Yep, lime water will go cloudy. Absolutely. Obviously tomorrow's live. I'll do exam questions, but like tonight I just logged on and thought, you know what, let's just run through some stuff. So no, you're right, midget. Yep. Anything that's solid in the thiosulfate practical. So if you go to the thiosulfate practical, wherever the hell the thiosulfate core practical is, what's the core practical? Is that a core prac? Yeah, that is a core prac. Okay, yeah, precipitate, boom, boom, boom. Yeah, whatever the solid is that forms in that practical is whatever it is what makes it go cloudy. So whatever's on the right hand side with an S. Probably like 8 o'clock tomorrow. You were saying ionic formulas. Listen, ionic formulas are really nice and easy. Look, if I say, let me just quickly go through ionic formulas. If I say, because you guys have got English tomorrow, so do you know what I mean? You might want to be getting some sleep. So if you're looking at sodium chloride, what do you need to do to work out a formula? Loads of people, there's loads of different ways to do it. Different teachers teach different ways. But essentially, look in your periodic table and find out what group number they are. So to work out a formula, whoops. So to work out formula, check group number. Write down ionic charge. Multiply ions if needed to cancel charge. So some people call it swap and drop. They do something called swap and drop. I'll show you both ways. Right, so if I know that sodium is in group 1 and if I know chlorine is in group 7, hopefully by now you guys know that means that sodium is in group 1. All metals form positive ions. They don't form negative ions. So will be +1. Chlorine will form -1. They cancel each other out beautifully. So the formula of sodium chloride is NaCl. But let's say we have something like aluminium. Oh, let's say we have aluminium chloride. I do the same thing, but this time I say, right, this is, and I look it up in my periodic table. That's group 3. That's group 7. This is a metal, so it's going to be +3. The group number tells me how many pluses to add on for the metal. The chlorine is -1. Now some people like to do, you can write minus or you can write -1. Some people like to say swap and drop. You just swap the numbers and drop them. So some people like that method and just say, whoopsie. So swap the 3 over to the chlorine and drop it down. And the formula is AlCl3. I just cancel them, so I just go, right, I need 3 -1s to go with a +3. That's the way I do it. But some people like the ionic formulas. It is group paper 1, but it's one of those skills that can come up in anything. So let me just show you something, one more of these. If you were asked for yeah, you're right, it's probably more paper 1, but it could come up. Oh my gosh, that's the worst bit of writing ever. Copper 2 nitrate. Does anybody know what this stands for? Does anybody know what the brackets in a written word with the 2 stands for? That's because copper doesn't have a group. Okay, in the current periodic table, the method we teach GCSE students, copper doesn't have a group. So we're telling you that it's a transition metal, so it can be copper +1 or copper +2. We're telling you by writing in the brackets there, this is copper +2. So we go, oh, thanks for that. Copper is 2+. You got to know your nitrate off by heart. You were talking about brackets. This is where you got your brackets. So copper's +2, nitrate's minus. You can just do a cancelling. I'm going to need 2 of these bad boys here to cancel out copper 2+. Or you can do the one people like to do, swap and drop. Swap the 2 from the copper over, drop it down, and that's the swap and drop method. But why would I need brackets? Check this out. I want to times this by 2, the NO3, put my 2 there. It looks like 32. I have to get some brackets in there. So that's when you're going to put your brackets in. Like that. CNO3 2. If the element doesn't, if it's a transition metal, they will always. Okay, one sec. I just lost that there. Okay. So. Yeah, it's a good question. Sometimes they do this. They love to do this as well. So they could say to you, okay, how would I know which one it is? Copper nitrate. Oh God, server keeps going mad. Right, so I would say to myself, right, I know off by heart that the nitrate ion is minus, and there's only one copper. So in this situation, the copper is just plus. So you always have to know the charge of one thing in a formula, otherwise you can't do it. So they want you to know these groups off by heart, like OH minus, SO4 2 minus, carbonate ion, CO3 2 minus. They're basically saying there's no method for that. You've got to know that there is a method, but not one that is worth learning now because it's A level. But those are group ions. At GCSE, they want you to know those 4 group ions off by heart and the ammonium ion NH4+, so that you can do that. Those 5. They want you to learn those group ions off by heart, and then if it's group 1, 2, or 3. They're always +1, +2, +3. If it's group 7, it's always -1. Group 6 is always -2, and group 5 is always -3. So you know those all off. Those are already set in stone. So, and then you just have to learn these group ions. Yeah, that's right. OH and an H from the other functional group is removed. That's right, newbie block. Yeah. Yeah, you guys feel free to duck out. It's getting late and you guys have got an exam tomorrow, so yeah. You could get asked to describe an experiment. I'll go over some of those core pracs tomorrow, like the sodium thiosulfate one in the rates topic. Yeah. Yeah, see you later, Ali. Good luck with the English. You've got to know all of those. Borosilicate, glass, soda, and lime. What's that in? Is that in a life cycle assessment or something? What is that? Let me check. Let me zing. What is that in? Resources, yeah. So if I zing back to resources, where's resources? Using resources. Yeah, I guess you are going to have to know that. NPK, you got to know. You got to know the fertilizers. N stands for nitrogen, P for phosphorus, and K for potassium. Composites. Yeah. So, yeah, it's just some memory recall there. So, yeah, in the resources topics, you got to know that. I'll go over that tomorrow, I think, because that's just like harbor process, water treatment. Yeah, you got to know that stuff. I could go to bed after this. Ooh, shit. Let's have a look at harbor process. It's literally just a sentence. So it's just like soda lime is made by heating limestone, sand, and sodium carbonate. Yeah, you got to know that. But what you want to do now, you just want to make sure you've got your exam in 2 days. You just want to make sure you have a little bit of knowledge on everything. Because if you have just a lot of knowledge on one or two things, then you need to be prepared, because half the stuff you revise they're not going to ask you, and half the stuff they are going to ask you. So it's like, it's best to know a little bit of everything, then you can answer every question, like you can score points on every question. So you've got to be more tactical. So with the harbor process, let me very quickly run through the harbor process for you guys. So a guy called Fritz Haber came up with this, and he won the Nobel Prize for this because obviously this has led to the massive increase in the world's population, like loads of food. So ammonia is used to make fertilizers and explosives. So yeah, it was like a really big thing. Right? Do you know what the sign in the middle means? Blah, blah, blah. Do you know what the sign in? Yeah. Not no. I don't think he was a Nazi. The thing with old Fritz, he went missing during the Second World War. Some people think he developed the gas that killed loads of British, French, and his own troops, the German troops as well, during the First World War. The British, the French, and the Germans were dropping poisonous gas on each other, and Fritz had developed that gas. People say, oh, wasn't one of his gases used in the chambers to kill people in the Second World War? Potentially, but he went missing on a train trying to escape Nazi Germany. So I don't know his full history, but yeah. Yeah, it means reversible. Yeah, absolutely. He died. I think he died before the outbreak of the Second World War. So, and I think he wasn't in favour of it, but they used some of his science. So, but yeah, mixed bag. Right. So this is a reversible reaction. This is the Haber process. Now, it's an exothermic reaction. So over here, when you have an exothermic reaction, you get a negative symbol like that. And I'd have to Google it because I can't remember. So I can't remember off the top of my head. I think it's 93. Who knows? I've just made that up, right? That is 100%. That is not right. But it's definitely a negative, and it's a few kilojoules are released, right? So it's exo. So the clue here is, I might just tell you it's exo. It's an exothermic reaction on the right hand side. I have my reactants, and I have my products. Awesome. So what you need to know is, as this is an exothermic reaction, I'm just going to go over theoretical or ideal conditions for Haber process according to Le Chatelier's principle. So if you was doing the Haber process, the fact that it's exothermic, so it's going to get hot. Now the way I think of it, okay guys, you mustn't write this in your exam, it's just how I do it in my head. I think of when they say exothermic, I think of that as hot. And that means that the other side of the reaction, as soon as I know that the one side is hot, I know the other side is cold. You're not allowed to use the words hot and cold. You have to say endothermic, exothermic and stick to that. But it just is the way it works in my head. If I know the right side is hot, then if I increase the temperature, Le Chatelier said, whatever you do, the reaction's going to do the opposite. So I want it to move towards the product. I want to make money. I want to get lots of yield, which means a lot of product, and that's ammonia. So I want it to move towards the hot side. So according to Le Chatelier, should I use a high temp or a low temp? What do you think? High temp or low temp? Yeah, I'm doing that. I'm going to go over that now. If I want it to shift to the hot side, I use a low temp. We use a low temp. Why? Because this dude Le Chatelier, he said, whatever you do to the reaction, it will try and counter the change. So if I make you hot, the reaction's going to say, hey, you're heating me up. I'm going to try and cool down. So it's going to go to the cold side. So if I want to encourage it to go to the hot side, I need to use a low temp. If I use a cold temperature, the reaction's going to go, oh, this is cold, I'm moving to the hot side. And the way we don't say the reaction's moving, we say it shifts in equilibrium. The proper language, technical language to say it's moving, we say it shifts in equilibrium, and we can say it shifts to the right or to the forwards or to the product. So you can describe either side of the reaction as product and reactant, or left and right, or backwards and forwards. So technically the products are on the right there and they're forwards, but you can choose the one that suits you best. Right, now the second thing we need to know, do I use a low or high temperature? Sorry, we just did temperature. Low pressure or high pressure? Does anyone know which pressure we use? What would be ideal, a low or a high pressure? Yeah. We're going to do compromise. This one, guys. Check out the title bit here. Absolutement. You're spot on about we can't use a too low temperature. These are theoretical conditions. We then have compromise conditions. So you need to know theoretical, and then you can discuss the compromise. So we actually know we want a high pressure here. Theoretically, we want a high pressure, and I'll go through why we want a high pressure. So we want to get rid of, it's not low pressure, we want a high pressure, and here is the reason why. If I just move my camera so my face isn't in the way, over there. How many molecules are over here? I've got 1, and then 3 lots of hydrogen and 1 lot of nitrogen. I've got 4 gas molecules. By the way, make sure that they say gas. Could have a solid or a liquid, and that's not going to be affected by pressure. So make sure these have all got a G next to them. They're all gases. So I've got 4 gas molecules here and only 2 gas molecules here. So if I use a high pressure, the reaction's going to say, hold on a minute, buddy, I'm going over there. I'm going to lower the pressure by reducing the amount of gas particles and reducing the number of collisions. So I'm going to reduce the pressure. So the ideal conditions are low temp and high pressure. Let's go to actual conditions, or compromise conditions. So in reality, they can't use 10 degrees. Some of you already said It's kind of triple, but you got a little bit of a mix there. Harbor process comes up in combined as well. In reality, for the compromise conditions, people have already said here, you can't use a low temp. Why can't you use a low temp? People already said it earlier. Why can't you use a low temp? Low temp means low rate of reaction. So you might get a high yield. It's like you might get perfect amount of ammonia, but it might take you 2 years and you ain't going to make any money. So you're like, hey, I don't care if I only make 10% ammonia and 90% stays as hydrogen and nitrogen, but I'm going to do it quickly, sell it and make my money. So you need a low temp means low rate of reaction. So we use a temp of 450 degrees, which is pretty high. So we actually take a crappy yield because we just want to make it quick, make the stuff quick. And also we use 250 atmospheres, means 250 times the pressure that's on your head right now. You'd be crushed if you walked into 250 atmospheres. You'd be squashed like a tin can. So it's quite a high pressure, but we could, why not 1,000? Well, high pressure is dangerous because of explosions. So safety is expensive. You basically need really thick walls, like 2 foot thick, if you're going to have mega high pressure, and that's very, very expensive. So basically, it's a compromise. We do use a high pressure, but we could go up to 1,000, 2,000 atmospheres, but then I'd need, the walls of my container would have to be so thick it would cost me too much money, and we can't use a low temperature because we'd slow the reaction rate down. But so you need to understand the compromise between what we should, what would be the ideal conditions and what we actually use. Yeah, 450 and 200 is ideal. That's right. Yeah, it'll be archived. So you just have to know with the Haber process that they're all gases. Nitrogen, hydrogen, and ammonia are all gases in this situation. Yeah. You can do English revision. I'll be revising tomorrow night. Yeah. Yeah. Phyto mining. Someone said phyto mining. So phyto mining is the roots of a plant. Those of you that, I don't know if you want to know what phyto mining is. Phyto mining, the roots of the plant suck up ions like copper ions, okay, when they're living on the soil. And what we can do then, we can take the plant and we can burn it. I know, pretty mean, right? Burning the plant, it's pretty deep. So what we do is we grow the plant first of all on low grade ore. So you grow the plant on a low grade ore, like the soil which doesn't have a lot of copper in it. And this is a way of us. So why do we do phyto mining? We do this because we're running out of copper in the real world. It's getting very expensive, and so we're trying to find copper from areas we wouldn't normally look. So looking at rocks that have hardly any copper, maybe only 1% or 0.5% copper, but if we put a plant on them, the plant will suck out the copper that it needs. We can then burn the plant into ashes, into black ash. So you're going to burn the plant and you're going to get ash. You've all seen cigarette ash or ash after a barbecue. So what are you going to do with the ash? You then go back to paper 1 and you're going to carry out electrolysis. You're going to dissolve and carry out electrolysis. That's the worst electrolysis looking thing in the world, but you get the idea, right? So you just need to know, carry out electrolysis to electrolysis on a solution of ash to remove the copper. So that's how we can extract copper, and that's supposed to be slightly more eco, because although you burn the plant and that releases carbon dioxide, you grew the plant, which took in the same amount that it's going to release when you burn it. So you haven't added any carbon dioxide to the atmosphere, and you haven't gone down a mine and used up some of our rare and running out copper ores that are running out. You've got copper from like mud or soil or some old rocks. Yeah. So the main thing with phytomining is you using plants, you're burning them, getting the ash, and then doing electrolysis. You're dissolving the ash in water and then doing electrolysis to remove the copper. Absolutely, Lloyd. Another way, better, much more economical, would be to take an old copper bike, or it could be an iron bike if you're extracting iron, and displace, or something more reactive. Actually, iron is more reactive. So take an old iron bike, which is slightly higher up in the reactivity series, scrap iron, throw it in there, or an I don't know, an iron plate or something made of iron, chuck it in there, and it will displace the copper. It will take the copper's place in the ash and push the copper out. So displacement is also good. Not sure if phytomining is in OCR. I don't know where my OCR book is right now. What's my OCR book? That's my EdXL. Oh, I can't locate it. Oh, there it is. Yeah, you've got to know phytomining and bioleaching. So it's very simple. It's like literally a 3 marker. So it will literally be grow a plant which will suck up the minerals, burn the plant to create ash, dissolve the ash in a solution, then use displacement or electrolysis to remove the metal ions. Displacement is obviously uses less energy. Electrolysis still uses electricity, so that's the little downside there. Let me just quickly see. Phyto. Yes, you do. You have phyto extraction. Yeah, you do. You've got phyto extraction. So yes, you have extracting metals by bioleaching or they call it phyto extraction, but it's essentially phytomining. So it is in OCR. I did the flame tests and I did the cations a little bit earlier. No. If you're doing OCR, those of you that are doing OCR, it's paper 2 AQA and paper 2 in OCR. ICE breadstick, it's paper 2 for AQA and paper 2 for OCR. Chemistry. There is another one. There's the other slightly green, more environmental phytomining is bioleaching. Have you heard of bioleaching? Exactly the same process. You're going to use electrolysis or you can use displacement at the end. So this ending is the same, but it's slightly different. So what you do here is bioleaching, you're just going to use bacteria and you don't burn them. So you just use bacteria. They absorb metal ions and release them in a leachate. So they're going to release them in a leachate. So instead of having the ash, you have a leachate, and then you just say do electrolysis or displacement to extract the ions from the leachate. So they're quite like, probably like 3 marks. I mean, you could get a 6 marker, which is both phytomining and bioleaching. So they both mean that you're conserving copper ores in both ways, and you're actually getting copper or metals from low grade ores that we wouldn't really use. I don't think really either one is better. You could evaluate them. Yeah, one uses bacteria, one involves burning plants. There's not really one better than the other, to be honest. They both, depends whether you use electrolysis or displacement. So you could kind of chemistry of the atmosphere. I've got a little video somewhere on chemistry of the atmosphere. The evolution of the atmosphere. Yeah, I've got a little video on that. I should put a link really. Hold on. 1 second, he says. 1 sec. Okay, I do have some videos with one sec. Okay. Okay, that's a video on the chemistry of the atmosphere there. That's a little 7-minute video with a couple of exam questions on the chemistry of the atmosphere. So I'll just put a link there. But basically, yeah, chemistry of the atmosphere, the world started out as volcanoes. I don't know if anyone wants me to go through it, or is there anything else anybody wants me to go through? Or you guys should really be getting down to some English revision for tonight. Is there any other topics anybody wants to go through? I can go through chemistry of the atmosphere if you want. Potentially you can use electrolysis for both as the final part to extract the ions from the liquid left over. So you can use electrolysis to get, or you can do displacement. Displacement is where you use an old piece of metal you're not using anymore that happens to be more reactive than copper. Say you were extracting copper, which is right at the bottom of the reactivity series. If you have copper ions in a solution and you throw in something that contains iron, like scrap iron, the wheel of a bike or something, it's going to steal whatever negative ions are in the solution and push your copper ions out. You'll see orange metal form. So you can use displacement, or you could just use electrolysis. But you can do that for both. With the leachate at the end, you'll need to, yeah. DNA, that's for the biology's done, isn't it? We don't need DNA anymore. B2's done. You're not having flashbacks, are you, Lloyd, to the horrible B2 exam? Are you doing triple or are you doing combined? Triple or combined, it depends. Are you talking about in polymers? Yeah, I went through a bit of the old polymers. Let's have a little look. I went through a bit of polymers. Yeah, it probably occurs in both. I didn't go over DNA, but I went over condensation, polymerization, but I didn't go through every example. But let's have a little look. I went through amino acids, and I went through diols and dioic acids a little bit earlier. Explained all of that. Let me just see. Yeah, there's a tiny bit on DNA. Let me just see if okay, so that is AQA. There's a tiny bit on AQA. Let me just see what OCR is saying on DNA, just to see if it's the same, because it probably is very similar. Where's your organic chem? Hydrocarbons. Oh, yeah, it's in AQA too. It depends. It depends what you're asking for. If you ask the DNA stuff, there's not a lot other than it's a double helix, and A goes with T and G with C, and there's cross links joining the DNA together. There isn't a lot of stuff, and that is just formed from condensation polymerization. So there's not a lot of detail. Like the actual understanding condensation polymerization comes before that. So yeah, you don't really need to know. I don't think you really need to know a lot. I don't. I literally think it is just. You just need to know that DNA. It's really the same as for bio. You just need to know that DNA is made up of two polymers, and that the individual monomers are called nucleotides. So monomers. My gosh, I can't even spell. The monomers are called nucleotides. DNA is a double-stranded polymer. DNA is made, what does that mean? Of two polymers. Okay, it's made of two polymers. There are monomers called nucleotides. Each nucleotide contains a base that forms a cross-link joining the two strands together. So there isn't a lot to know there, just that like where on here, if I have an A here, I have to have a T here, and they actually form an weak intermolecular force called a hydrogen bond between them. And if I have a G, here, I'm gonna have a C here. And each monomer, each single unit of DNA has one of these letters called bases. But you really just need to know it's a double helix, it's two strands. There's monomers called nucleotide that make up the polymer that's DNA. DNA stands for deoxyribonucleic acid. It's a polynucleotide. So it's a long strand. But yeah, there's not a lot to know there. Somebody asked about evolution of the atmosphere. Are they still about? Or have they gone to bed? Who asked for evolution? Midlage asked chemistry of the atmosphere. Are they still about? Or I hope you guys do well in your English tomorrow. It's yeah, good luck with that. Is that your last English? That must be your last English exam, unless you got further. I know some people have got further maths the week after. Most people are finishing this week. Some people have got further maths next week, which is going to be pretty horrible because all their friends are going to be on holiday. So that's pretty deep. Yeah, there's always the next paper, so right, guys, is there any other science topic, a quick topic anybody wants me to go through? Otherwise, I'm going to hit the bed because tomorrow I'm going to be doing a live, and you guys should probably be bussing out your English revision or getting a nice early night so you can wake up. There's no point in, you want to be fresh, you don't want to be flopping because you're not fresh. So tomorrow night I'm doing a live. I'm going to start at 8 on Monday, and yeah, 8 till late I'll be doing a live for chemistry. But yeah, Alright guys, I'm going to end the live now. So see you guys later. Tomorrow night at 8 I will... Oh, how to obtain potable water. Someone's put up a question, so I'm going to zing through potable water. I actually got a video on that. On how to do potable water. Let me put a link to my video. I've got like a 60-second video short on potable water, so I'll put a little link here. And yeah, that's totally cool, man. Like you know, it's not an issue at all. Let me show you my potable water. Okay, where's potable water? Is that... yeah, actually, whoa, what I need is share, copy, back here. Where the hell is this? On the chat. Okay. Alright, this is like there's a video on potable water. So if you click on that video, that's like a 60-second, but I can zing through potable water for you live now as just really easy. So let me go through, I'll go through potable water, but you can always, I've got quite a few like little short videos you can just like watch on your phone. They're designed so you can watch them on your phone. So potable water, first of all, do you know what potable water is? So the question is, what is potable water? Anyone know what potable water is? So the first thing to know is drinkable water. It is safe. Yeah, safe to drink. Perfectoid. Yeah, it's not that it has nothing dissolved in it. It does have stuff dissolved in it, like so Liber, it does have stuff dissolved in it, but it's safe to drink. It's either been treated or it's naturally safe to drink, like a spring that has the water. So what do we do? Where do we, in the UK, where do we get our water from in the UK? And the answer, of course, is the rain. So when it rains, water collects. You need to know these two terms. Water collects as ground. Let's do surface water. Does anyone know what surface water is? Surface water lies on the surface of the earth. So in rivers, lakes, and reservoirs are where women and men have dug out holes in the ground so that when it lakes they can collect a giant lake of water. There'll probably be a reservoir somewhere near where you live or somewhere in your area that will supply your tap water. So that's called surface water. Other rainwater collects in aquifers. 2,000 years ago, the Romans learned how to get fresh water from aquifers. So they learned that deep underground there are lakes of like water that's trapped underground, and they drilled down and got that. When you make a well, you lower a bucket down or something, you're going down to an aquifer. So other rainwater collects in aquifers under the ground. Yeah, groundwater in aquifers. Yep. Cool. Now what you're going to do, you're going to treat it. And the first thing you do is filtration through a mesh. So you go filtration through a mesh, and that removes twigs. Whoopsie. That removes twigs. Again, my video will explain this a lot quicker than me doing it here. But yeah, so filtration through a mesh removes twigs. Then you filter with sand and stones. You can actually do this at home if you get water. If you were desperate and it was like, I don't know, the government had collapsed and you were in a country and you were like where there's no government and there's no sanitized water, you can actually filter water through a mesh to remove stones and sticks, and then through sand, and you're going to get other bits of mud, bits of grass. You're going to get other stuff out of the water. So then you filter with sand and stones or gravel, and then finally you're going to kill bacteria. As long as you kill the bacteria, it doesn't matter what it tastes like. So then how do we kill bacteria? You need to know there's 3 ways to kill the bacteria. What can you kill the bacteria with in the final part of making potable water? And this is why tap water, you can sometimes taste it. Chlorine, like in a swimming pool, we add chlorine to our tap water. Yeah, sterilizing it's called. That's absolutely right, Raja. Yeah, chlorine. We can use ozone from the ozone layer. That will kill any bacteria. And we can use UV light. So, whoops, I don't know why that came out in capitals. We can use ultraviolet light. So, this is why, you know, in your bedroom, when you've not opened the curtains in a week, that's not good for bacteria in your bedroom. Essentially, ultraviolet light, opening your curtains and letting sunlight into your room will kill bacteria that's on your bed or living in your room. So you can sterilize water by shining intense ultraviolet light into the water. You can buy UV torches online and sterilize water like that, but you'd need a pretty intense one to actually do a good job. So you can use chlorine, ozone or UV light, and that's sterilizing the water. Now it's safe to drink. That's what we do in the UK. And that's the final step. So really, what do you need to know? Filter it. Collect the ground or surface water. You need to know which one is ground, which one is surface. Groundwater is under the ground. Surface water is in rivers and lakes. Filter it through a mesh to remove sticks, stones, leaves. Then filter it through sand and gravel, and then sterilize it using chlorine, ozone or UV light. Now also, if you live in a hot country like Kuwait, Saudi Arabia, Dubai, they're not just hot, because the Amazon rainforest, Brazil is hot and they got plenty of groundwater. It rains in the rainforest, would you believe it? So it's not just hot, it's dry countries. So if you go to Saudi, Dubai, United Arab Emirates, wherever, it's dry. How do they get water? So you need to know that in the hot, dry countries, they use something called desalination. And desalination is where they boil the seawater and they then condense it and remove the salt. So they take seawater and remove the salt. Now, this is quite expensive to do in the UK, and we're lucky we don't have to do it. It rains all the time here, so we don't even think about it. But in those dry countries, they have to spend a lot of money to get water because they've got to boil the water and remove the water, and then they leave the salt behind, and now they can drink the water. So that's called desalination. And there's a third way to get fresh potable water, and they do it in countries where they use seawater. It's called reverse osmosis. You just need to know the name. It's called reverse osmosis, and it uses a membrane to let water go through and leave the salt behind. It's called reverse osmosis because in osmosis, water normally moves from a high water concentration to a low. But in reverse osmosis, you want the water to move away from the low concentration to a high. You want all the water to go out and be together over there, leave the salt behind. So they call it reverse osmosis. And that requires energy to do that. Someone said, what's the difference between chlorine and chloride and when do they exist? So, yeah. So, Cl2 is chlorine. Now, when a chlorine atom is on its own, it's diatomic, like all the halogens. They are in group 7, so they're going to covalently bond to themselves like this, right? And this one over here, we use dots and crosses. Make sure if it asks you for dots and crosses, you use dots and crosses. Right, 2 chlorine atoms covalently bonded, that is called chlorine. Whoa. So that's chlorine. That's a halogen. Okay. So little clue, it's a halogen, it's chlorine, it's a gas at room temperature, a light green or yellow green gas or pale yellow gas, any of those colours will do. And that's at room temperature. That's chlorine on its own as an element, okay? Chloride, which your question was, is something completely different. Chloride, yes, it sounds like chlorine. It's known as a halide. And it's a chlorine atom that has decided not to covalently bond with itself, but instead, chloride has stolen an electron to become Cl-. Now, you can only do that when it's in solution. You can't have an ionic gas. A gas can't be an ion. They have to be dissolved in water, dissolved in a solution to become an ion. And this chloride ion will have AQ next to it, so you know I'm dealing with chloride, or they'll call it a halide, and it'll look like this. And the difference here is that it's stolen an electron and it's an ion, so it's like that. It's on its own like that, but it's not going to be on its own. If it's stolen an electron, guess what? Somewhere in the solution, in the AQ, is the thing that it stole the electron off. So probably lithium chloride, maybe sodium. If you've got salt water, you'll have sodium and chloride ions. There'll be something that it stole the electron off that's become positive. So it's not just going to be on its own. You just don't get a solution of chloride ions in water. There'll be chloride and sodium. There'll be a positive ion that goes with it. And you do need to know that there's a different test for each of these. So if you're doing this test, this is damp litmus paper, red, then bleaches white. So chloride ions will not bleach damp litmus paper red then white, okay? They have a different property than chlorine gas. So chlorine gas has a different property than chloride ions. Chloride ions, we do the halide test. The test for halides, we add silver nitrate and nitric acid. We get a solid white precipitate of AgCl with a S. So they're two different things. Yeah. So they're two different things, those. Really good. So it's chloride. It's chloride. We all call it chlorine, but it's chloride in the swimming pool. We all call it chlorine, but we all say, oh, the chlorine's hurt my eyes. But if it was chlorine gas, some chlorine gas is leaving the water. You can smell it. When you walk in a swimming pool, you are smelling the chlorine gas coming out, but it's actually chloride ions. They put a solution in with chloride ions in there, and you get some chlorine gas forming as two of the chloride ions maybe bump into each other or whatever, or you know, there's some chlorine gas coming off as well, so some of the chlorine ions are turning back to atoms and forming chlorine gas. But yeah, we do say we put chlorine in water and we put chlorine in swimming pools, but technically once it's in the water, it's not a gas, it becomes an aqueous ion. So yeah, but yeah, it's complicated. So we use chlorine. You would say, if you're asked for sterilizing, we just say use chlorine for sterilizing. Cool. Right. I went through the Harbour process about 20 minutes ago or something. If you zing back on the video, about 20 minutes I went through the Harbour process. I have up, there's a couple of videos I've put on here. Alright guys, I'm shooting off because tomorrow I'm going to do a live from 8 o'clock. So yeah, I'll see you guys tomorrow. Good luck with your English exam, guys, and nice one. Good luck with English.